by building our reactions before we balance it. So in the last class, our reactions were already made for us, right? They already gave us the compounds. So now we're going to build our compounds based on a written version of them, and then we're going to be able to balance them. Okay? So go ahead and get this written down if you need to, but we're going to write down the chemical compound of it. So you might need your periodic table of ions out, because we're going to have to build those compounds. Okay? Okay. Is zinc one of our diatomics? No, right? Remember the diatomics on the periodic table make that little 7, right? NOFCl, Bri, those are our diatomics. They have to exist in pairs, and then plus hydrogen, right? So zinc is not one of our diatomics. So when we're building our reaction, is this one of our reactants or one of our products?
No, which one?
Zinc and hydrochloric acid. Are they our reactants or our products? They are the reactants. They're what we're starting with. So that means zinc plus, okay, I might want to leave some room for coefficients here. Zinc plus hydrochloric acid. What's the chemical formula for hydrochloric acid?
HCl.
HCl, good. HCl. And that produces zinc chloride and hydrogen gas. Okay, so what do we know hydrogen gas is? H2, right? It's not just H, because hydrogen is one of our diatomics. It has to be a pair. When it's by itself, it has to be a pair. What is the formula for zinc chloride? What's the charge on zinc? +2, and chlorine is -1. So if I cross these down, right, that gives me ZnCl2. Okay, so that's what needs to go in our chemical formula. Do you see how we formed this? Yeah. Okay, so it's not just putting ZnCl, right? That's not necessarily zinc chloride. We got to make that ionic compound balance. Okay. So now we balance our whole equation. Okay, we have zinc, hydrogen, and chlorine. Okay, and we want to balance our whole chemical formula, chemical equation. Okay, how many zincs do I have on the right-hand side? 2. On the right, I'm sorry, on the left. I will start on the left. That's my bad. 1 on the left. How many hydrogens? 1. And chlorines? 1. Okay. On the right-hand side, how many zincs? 1 chlorines, 2 chlorines, and how many hydrogens? 2. Okay, so I need to get another hydrogen, another chlorine on the left, so that's it, right? That would make this 2 and this 2. Okay, so we match, we match, we match. Pretty easy, right? The part that I want us to pay attention to is how we built the whole compound, right? So naming and building those compounds, we're not quite done with that. We have to be able to build that chemical reaction based on the word forms given. Okay, does that make sense? Any questions there? How did the balancing go on the assignment? Okay, pretty good? Okay.
The last ones were kind of hard.
On all of them, no, we don't have to put plus H2 on all of them. This tells us that it yields hydrogen gas. That's one of our products. Yeah, good question. Okay. All right, let's try another one here. We'll do this one together. Magnesium and hydrochloric acid react to produce magnesium chloride and hydrogen gas. That seems pretty similar, right? Is magnesium one of our diatomics? No, so we don't need anything except Mg. Okay. Plus hydrochloric acid, right? We know that was HCl. We knew that from our last one. Okay, now we have to build magnesium chloride. Mg is what charge? +2, right? It's in group 2, so it's got a positive 2 charge. Cl is -1. So again, we're going to cross these down. It's going to look the same as zinc chloride, MgCl2, plus hydrogen gas, which we know is H2. Okay. So that looks exactly the same as our last one, right? How are we going to balance it then? Yeah. We want a 2 in front of our hydrochloric acid. I'm still going to check to make sure, right? I've got 1 magnesium, 1 magnesium. I've got 2 hydrogens now and 2 hydrogens, and 2 chlorines and 2 chlorines. Okay, so I'm still going to check myself to make sure that everything goes right. This was just an example of, they looked pretty similar. Okay? Questions here? Let's go ahead and have this last one. You want to try one on your own? Yeah. What's it mean to be aqueous? That's right. It means it's dissolved in water. That makes no change on how we write the compound. We're still going to write it as nitric acid. Okay? So we're still going to write nitric acid. It reacts with magnesium hydroxide. It forms magnesium nitrate and water. Okay? Can we go ahead and do this one on Rihanna, or do we want to do it together?
I guess we'll try.
How about I'll just do it on the board, and if you want to do it on your own, you do it on your own. Okay. All right. If you want to try it on your own, go for it. Otherwise, we'll do it together because we weren't quite sure. Nitric acid. Do you remember our rules for naming acids?
No.
No.
It is. It's gonna have OU.
8. It comes from an 8 ion. So nitric acid means it comes from what? Nitrate. Nitrate is NO3 minus 1. So how many hydrogens do I need to pair with that to make it an acid? Just 1, right? So then I can get rid of my charge. Don't leave charges in chemical compounds. Okay. So nitric acid reacts with magnesium hydroxide. So let's think about this. Magnesium is a +2 charge. Hydroxide is OH. What's the charge? Good, very good, -1. Okay, so when I cross these down, can I leave it like this? MgOH2. I have to have parentheses here, so I know that 2 goes to the whole hydroxide molecule. Okay, so I got to put parentheses around that OH. Okay, and that's because we need 2 hydroxide molecules. We don't just need 2 hydrogens. We need 2 hydroxide molecules. So this is going to go here. MgOH2. Says it forms magnesium nitrate and water. Okay, magnesium nitrate. Let's think about what that looks like. Mg is +2. Nitrate is NO3 minus 1. So we're going to cross those down. That would give us Mg parentheses NO3 parentheses 2. Right? Do we agree there? Okay, and our last product is water.
Just because it says
It forms magnesium nitrate and water, yeah. Okay. Any questions about how these compounds were built? Okay, because this is a skill that you will have to be able to do, is take it from word form and put it into a chemical equation. Okay. Any questions there? So is it balanced? Way too hard to tell from just looking at it. Okay, so let's go ahead and balance this. I have hydrogen, I have nitrogen, I have oxygen, and I have magnesium. But here, look, hydrogen and oxygen are in both of our reactants. Does that mean we need to write it twice in our list? No, we just have to count it both places. Okay? All right, let's go ahead and count these. How many hydrogens total do I have on the left side, the reactant side? 3, right? 1 here and then 2 here. So I have 3 on the left. How many nitrogens? 1. How many oxygens? I have 3 right here in nitric acid, plus 2 more, which gives me 5 total. And magnesiums, how many do I have? 1. Okay, let's look to the right side now. How many hydrogens do I have? I just have 2 right here in water. Nitrogens, I have 2. Good. Oxygens. Yeah, good. 6 right here, plus 1 on water, which is 7. And magnesium, I have 1. Okay. So remember when I talked about how if we have an odd number on one side and an even number on the other side? yeah, we got to get those to match, right? So here, if I look at my hydrogens, I have an odd number on the left, yet an even number on the right. So can my product side ever have an odd number of hydrogens? No. Okay, so that means I'm going to have to get this side to be even somehow, right? So what would be my first probably step to do that? Yeah, I want to try to double that, okay, or give that an even number of hydrogens, and we'll see what that does for us, okay? That gives us 1, 2, 3, 4 hydrogens total. It gives us 2 nitrogens, and it gives us how many oxygens? 6 plus 2 more, which is 8. Okay, so now I'm not balanced. My magnesiums are still balanced. I need 2 more oxygens and I'm sorry, I need 1 more oxygen on the right and I need 2 more hydrogens on the right. So what could I do with that? Yeah. So that gives me 4 hydrogens and it gives me 2 oxygens here plus 6 oxygens here, which is 8 total. Okay. Question. Now 4 different types of reactions. And we can tell the type of reaction that it is based on the chemical equation that we're given, okay? So the first type of reaction is called a combustion reaction. Have you heard that word before? Yeah. Combustion. Where have you heard it most of the time?
In relation to fire.
In where? Science. Okay, yeah. Where else? Okay, yeah, and an engine, right? You hear about combustion engines. That's kind of the most common. I don't know anything about engines, so I in no way can explain that to you. But I think it's a thing. Okay. Combustion happens when oxygen gas combines with what we call a hydrocarbon, which is C something, H something. Okay. C and H combination is called a hydrocarbon. Really original, right? And the products of a combustion reaction are always going to be carbon dioxide and water. Always. Okay. So in a combustion reaction, if we have carbon dioxide and and water as our products, it's always going to be a combustion reaction. Okay? So this would be an example of a combustion reaction. You can write down the example. You don't have to. That's up to you. But we always start with some form of a hydrocarbon, right? C10H8. A hydrocarbon could also be CH4 or C2H6 or C6H8, whatever it is, it doesn't matter. These are all considered hydrocarbons, okay? And they are going to react with oxygen gas, which would form carbon dioxide and water. Okay. So combustion reactions, I think, are the easiest to pick out. It has a guaranteed product, right? 3 of them are guaranteed what they look like. Oxygen gas, carbon dioxide, and water. The hydrocarbon is the only one that may be a little different, right? And it's just going to have the subscripts change. That's it. Okay, so combustion, I think, is the simplest to pick out. Synthesis. What does it mean to synthesize something? Yeah, to make, right? To make it. So a synthesis reaction is when 2 or more simple compounds combine to make a more complex molecule. So a new complex molecule is being made. Okay, and so this is the very base formula for a synthesis reaction. Some compound A plus compound B forms compound AB, right? It's a combination of A and B. Okay, so that's the base formula for a synthesis reaction. And then I gave you just an example. Okay, iron plus sulfide yields iron sulfide. Okay, really riveting stuff here. Okay, so synthesis means to make. So when we see 2 simple compounds making a more complex compound, that should make you think of a synthesis reaction. Okay? On the opposite side of that, what's it called when something breaks apart? What would be a word for something breaking apart? Breakdown. What'd you say? Decomposition. Perfect. That's the next one. Decomposition reaction is when something breaks down. So we take a complex molecule and we break it into 2 simpler molecules. Can you hopefully take a guess at what the base formula might look like? Rachel, what do you think?
AB yields A plus C.
Perfect. Okay, so we're taking a complex molecule, we're breaking it down into two individuals. So here's an example of that. Right, when we break down water into hydrogen and oxygen again. Okay. Synthesis and decomposition reaction you need to kind of think about as complete opposites, right? One is where something is made, one is where that complex compound is being broken down. So we make one, we break one. Okay, our last type of reaction kind of has two parts, so we might have 5, not 4, like I said. Okay, do we have what we need here? All right. Our last type are called replacement or displacement reactions. Okay, so this is a single displacement reaction. And it's basically where one element is traded from one compound to another. Okay, we trade either, the cation from one compound to the other or the anion from one compound to another. Okay, so single displacement is where we see one of our elements kind of trade places. Okay, so in our base formula it says A plus BC yields AC plus B. So what's our compound here that's been traded? C. C has been displaced, right? So here's an example of that. Okay, so in this reaction, magnesium plus water yields magnesium hydroxide and hydrogen gas. What's our element that's been displaced or been traded? Yeah, oxygen, but yeah, an OH molecule as a whole. Okay, that one's a little trickier than a simple single displacement, but we see oxygen specifically has been traded, and it brought that H with it. Okay. All right, our double displacement, I think, is kind of another easy one to spot because our cations and our anions completely switch places. Okay. So this is a double displacement where both of them switch. Makes two completely new compounds. For a double displacement reaction would be AB plus CD yields AD plus CB. Okay, so once we have this written down, I want to talk through this double displacement a little bit because we're going to work with double displacements a lot. Okay, so once you have that written down, I'll help you through that a little bit more. Within chemical compounds, which comes first, the cation or the anion? The cation comes first, right? The cation is on the left side of the periodic table. The anion is on the right, right? And when we put our compounds together, we always work left to right. Is that ringing bells? Mm-hmm. Hopefully. Okay. So this is the cation and the anion. The cation and the anion. Okay. So when we are looking at this double displacement reaction, what happens is that we completely switch places. So we take the cation from one and the anion from the other and build a new compound. And we take the cation from one and the anion from another and make the new compound. Okay, so that's how they'll always switch places. But you should understand, when we rewrite this one in the middle, this BC, we're not rewriting it with the B coming first and the C, right? Whenever we write those compounds, the cation still has to come first. So even though B and C are combining, we still have to write them in the correct order. Cation plus anion. Okay, that makes sense? Hopefully? Okay. Very good. So here's an example of a double displacement reaction. Okay, we see lead nitrate plus potassium iodide yields, that's not lead. Yes, it is. Yes, it is. I'm losing it. Yields lead iodide plus potassium nitrate. Okay, so all they're doing is just switching those places. And you can see it works for polyatomic ions too, not just single elements, right? This whole polyatomic ion switched places and paired with potassium this time. Does that make sense? So it's the whole cation and the anion, regardless of whether it's an element or a polyatomic ion. Okay? All right. That is it for Chapter 8. Chapter 8 is very, very short.